Okay. So we were discussing the three ideal elements in case of translational elements. So they were mass, friction, and the spring. Okay. So I hope you have understood the notations used here. So F, capital F always throughout this module it's going to represent the applied force, and in case of mass, okay, the capital M is used to represent it. X represents the displacement, and whenever the force F is applied, you can imagine that the mass is going to be displaced. Okay, so when it displaced, so that displacement will be represented by X, and at the same time it is associated with some friction also. Okay, so therefore now the friction is represented by F equal to B into dx by dt. But if the friction is associated with at both the ends, okay, so then we have differential equation, that is B into dx1 by dt minus dx2 by dt. We have to take the difference of the displacements between the two ends. Similarly, the third element, spring, for this also, if the displacement is only at the one end, it will be F equal to k into x. Or if that elasticity, okay, so experiences displacement at both ends, so it will be written as the differential thing, that is k into x1 uh, minus x2. So these are the three ideal elements related to mechanical translational elements. So similarly, whenever a force or a torque is applied, the mechanical elements are put into rotation. Okay, so those systems are known as mechanical rotational systems. So now let us see what are the three ideal elements present in the mechanical rotational systems. Okay, so now we will write mechanical rotational system. So now in this also we have three ideal elements. So one is mass of inertia or moment of inertia. Mass of inertia. So this element is represented by J. Okay. The second element is again, it is the friction only, or the damper element, friction or the damper element. Okay, so this is also again represented by capital B. There is no change in the notation. And the third one is here, the torsional spring. So torsional spring. So here also the notation will be K only. So only thing is that the kind of force that is applied will be different. And here, in case of rotational elements, okay, so the elements are applied a torque T. Okay, so this torque is the one which is going to put these elements in rotation or in rotary movement. Okay, so therefore, we will write the force balance equations, which are now called as torque balance equations in case of rotational elements. So therefore, let us individually consider the three elements J, B, and K, and we'll write the torque balance equations for them. Okay. So first one is the inertia element. First one is the inertia element J. So what is the torque balance equation uh, for this? Okay. Now, when the torque T is applied, this moment of inertia, Okay, so which is nothing but it's the property of the system which stores the kinetic energy in a rotational systems. Okay. Um, so here this is actually analogous to the mass in case of linear motions. Okay. Uh, this inertia element J can be now modeled uh, like this. So here assume that this is the shaft connected and this is the element J, and this is again the shaft part. Now this element J is applied with the torque T. Now because of this the mass will be put into the rotation. So J is a inertia, mass of inertia. To this the torque T is applied. Because of this now this mass of inertia is put into rotary movement and it is moving with an angle theta. Okay, now it is exactly opposite to that of linear system. So in linear motion, you can now recall that we used to apply force F to the mass M. Because of that, it was displaced by X. Okay, now in case of rotational elements, the mass is now is called as the moment of inertia or mass of inertia, and that is under the influence of applied torque T. And due to this T, that particular mass or moment of inertia starts rotating at an angle of theta. So all these informations are shown in the simple block diagram. So now because of this, that mass of inertia is going to oppose the torque T, and that T will be proportional to, okay, alpha. Okay, so or T will be equal to J into alpha, or T is equal to J into, so d omega by dt. It is angular displacement. Okay, so simply here omega represents the angular velocity, and next when this angular velocity is further differentiated, okay, so you can further write that t is equal to j into d by dt of, for omega you can write d theta by dt. Okay. So therefore t will be equal to j into d square theta by dt square. Okay. So here whenever the torque T is applied, the moment of inertia will be under angular acceleration alpha. Alpha represents here angular acceleration. So therefore T is proportional to alpha, or T is equal to J into alpha. Okay. But this J into alpha can be further now replaced by substituting for alpha. So here alpha, which is nothing but angular uh, acceleration. Okay. So you can now replace it. So alpha is d omega by dt, or as omega is equal to, d theta by dt, then t is equal to j into d by dt of d theta by dt, or t equal to j into d square theta by dt square. Okay, so therefore alpha is the angular acceleration, and here omega represents the angular velocity. Okay, and what is this theta? Theta represents the angular displacement. Okay, so theta is the angular displacement. It is just analogous to that x in case of linear movement, and then omega is the angular velocity, and alpha is the angular acceleration. Okay, so that's why first we are writing t proportional to alpha, or t is equal to constant j into alpha. Okay, so this acceleration is nothing but rate of change of angular velocity, that is d omega by dt. So here I'll write alpha is nothing but d omega by dt. That's why we are replacing it. But further, angular velocity is nothing but it is the rate of change of angular displacement. Okay, so that's why d by dt of d theta by dt. We are just replacing, that's all. This acceleration by angular velocity and angular velocity by angular displacement. So finally, t is equal to j into d square theta by dt square. Okay. So you just can compare these equations even with the previous mass also. So for mass we used to write what? F is proportional to m into d square x by dt square. This was for the mass which was under linear movement. So now this is moment of inertia which is under rotational movement. That's all. So the mass m is analogous to j. Okay. So x here represents theta in this case. Okay, and F here is analogous to the applied torque T. So therefore, in case of rotational system, the applied force F makes the mass to move in a linear manner, whereas in case of rotational systems, the applied torque T is going to make the moment of inertia to rotate. That's only the difference. So further, in case of translational element, we have the linear displacement x, whereas in rotational systems, we have the angular displacement theta. Okay, so in previous translational system we have uh, the velocity v. Now in this case we have angular velocity omega. Similarly, a was the acceleration in case of translational system. Now here we have alpha as the angular acceleration. Okay, so therefore every element has got its analogous equivalent in case of rotational systems. So now this was the first element. The second element is again the damper or the friction. So let us write for the friction. So even though mass of inertia is associated with the torque, still the J is going to experience some friction or the damper element. So the damper element. So now here the same symbol is used for the damper or the friction. Assume that at one end it is tied up, it is connected to the reference, and here we have applied the torque T, and because of this there is theta. Theta is nothing but angular displacement experienced by that mass of inertia, that is J element. Okay. So this is B, that is friction associated with it. Okay. So now for this we can write T will be proportional to uh, d theta by dt. Or you can write T is proportional to first omega, or T is proportional to omega is nothing but d theta by dt, or T will be equal to V into d theta by dt. Okay, so I'll write once again what are the meanings of this. Theta represents here angular displacement. It is displacement only, but in the angular pattern. That's all. Okay. So then here omega represents angular velocity, and we have one more term alpha. Alpha represents the acceleration. Angular acceleration. That's all. Okay, so that's why. So when torque is applied, so whatever the moment of inertia J is there, it is going to experience some friction. So that friction T, okay, this will be proportional to angular velocity. Okay, or T is proportional to, you can write d theta by dt, or T will be equal to B into d theta by dt, where B is the friction coefficient or the friction constant. Okay. Now this is when the friction is associated with the element at only one end, that is the theta is present only at the one end. So whenever the friction associated will be at both ends, just similar to the previous case. Okay, so we will next write a modified equation. So that is, for the same damper element, assume that the torque T is applied, but this end angular displacement is theta 1, whereas the other end angular displacement is theta 2. That is, at the two ends, two different displacements are there. Okay, so now in such a case, so we will have to take the differential angular velocity. That is, we have to consider differential angular velocities. That is, in this case now applied torque T will be proportional to d by dt of theta 1 minus theta 2. Okay. So this is what is the uh, expression in case of friction element or the damper which is associated with the two different displacements, or you can simply write T is equal to B into, okay, d theta 1 by dt minus d theta 2 by dt. Okay. So this is the uh, final equation. Okay, so experiencing, that is damper element experiencing angular displacement at both ends. Okay. Next, the third element what we have is the spring. Now in this case it is called as the torsional spring because uh, in earlier case, that is in case of translational elements, whenever force was applied on the spring, okay, then the spring used to give an opposing force. Now in this case, when the torque is applied to the spring, okay, the spring is put into a kind of rotational twist. Okay, so therefore it is called as the spring or torsional spring. Or simply you can write as spring only. Okay. So now in this case, the representation is again, the symbols won't change. Here also we are using the same symbol to represent the spring and same constant also K. The only difference is now instead of F, now T will be applied, torque will be applied, and then resulting we have theta, that is angular displacement of the spring. Okay. Now the equation for this will be, so T will be proportional to angular displacement, that is theta, or T is equal to K into theta. T is equal to K into theta. Okay. So now because of the torque, the spring will be twisted. Okay. So therefore that is a torsional spring. And that opposing force given by that spring for this T will be proportional to theta. So we can write T equal to K into theta. Now when the same spring, okay, so experiences two different displacements for the applied torque, that is theta 1 at one end and theta 2 at the different end. Okay, now we have to consider the differential displacements. So in this case, T will be proportional to theta 1 minus theta 2, or T will be equal to K into theta 1 minus theta 2. So now you can just compare these equations with the previous translational system equations. Okay. So there we had what, instead of T there was F equal to K into x1 minus x2. Okay. So all these elements are concerned with the linear displacement. Okay. So whereas in case of rotational systems, so elements are put into rotational movement. Okay. Because of the applied torque T. So therefore instead of x we have to write angular displacement theta. Instead of force F, we are writing the torque T, and the spring constant will be, if K is a linear spring, this K in the rotational system, K will be known as torsional spring. Okay, so therefore these are the three ideal elements in case of rotational system. So therefore here also we are going to uh, list the important symbols that we have used in case of rotational systems. Okay, so therefore list of symbols. in mechanical rotational systems. In mechanical rotational systems. Okay. So the very first one we will take theta. So theta here it represents the angular displacement. Angular displacement. Next what we have is omega, which is nothing but d theta by dt. Okay, so this is called as angular velocity. Angular velocity. So next what we have is alpha, which is d square theta by dt square. This is angular acceleration. Angular acceleration. So other than this, we have the elements, that is T, which represents the applied torque. Applied torque. Then we have J, it is called mass of inertia. Mass of inertia or moment of inertia. And then we have B, which is nothing but the rotational friction coefficient. It is rotational friction. Rotational friction coefficient. And next K, it represents again stiffness of the spring. Stiffness of the spring. Okay. So therefore, we have the symbols theta, omega, alpha, T, J, P, and K in case of mechanical uh, rotational systems. Okay. So therefore, now collecting these, we can write a comparison or a table-like structure or a summary. Okay. So you can write a summary for these two systems. Okay. So here I'm writing a table showing analogous elements. Okay. So table which is showing analogous elements. Analogous elements. So on one side I'm going to write mechanical translational systems. Translational system. On the other side we have mechanical rotational systems. Rotational system. Okay. So here in the case of translational systems, we have the mass m, but whereas in case of rotational systems, we call it as a mass of inertia, that is j element. Similarly, in case of translational system, we have the friction B. So here also we have the same friction represented by B only. B only. Third, we have the linear spring K, whereas in case of rotational elements we have torsional spring. Torsional spring K only. Symbols are same. And next, if we apply force F here, in case of rotational, we apply torque, torque T, torque T. Okay. So fifth one is uh, we have displacement in case of translational systems, whereas we have angular displacement theta in case of rotational systems. Okay. So still we have uh, two more things to write. Next we have the velocity. In case of translation system, velocity v is equal to dx by dt. Whereas in case of rotational systems, we have angular velocity. We have angular velocity written as W equal to d theta by dt, or omega equal to d theta by dt. And next what we have is acceleration d square x by dt square in case of translational system, whereas in case of rotational we have angular acceleration, that is alpha um, d square theta by dt square. Okay, so here you can acceleration a, it is a in case of translation. Here we are representing it by alpha, that's all. Okay, so angular acceleration, angular velocity are nothing but these are nothing but the velocities or the accelerations gained by the mass of inertia whenever they are put into rotational motion. That's all. Okay. So assume that you have a thread here and you have fixed a mass. Okay. This J element, inertia element. Okay. So when the torque T is applied, okay, so it starts rotating around this hinge. You can. Okay. So therefore, whatever the displacement we have from this position to this position, okay, so this is called as the angular displacement theta, that's all. Okay, so whereas in case of what translational systems, so if you have the mass m, if you apply the force here, okay, so it's gets displaced linearly. Okay, so and this displacement we represented by x. So here no angles are associated, but here angular motion is associated with the mass, that's all. Further, even though it is in the angular movement, okay, so friction is also associated, uh, b is also there. At the same time, this particular mass of inertia may be deformed also. Okay, if it is having some elastic property, it may be deformed also. That's why we have both b and k associated with the j. So only difference is this j will be under rotational movement, that's all, instead of linear movement. Okay, so that's why we have totally two different broad categories in case of mechanical systems as translational systems and rotational systems, depending on the method in which they are put into motion because of application of linear force and the rotational torque. Okay. And this is the summary of these three elements and showing the analogous properties. Okay. So in the next session, so I am going to write the electrical systems. Okay, we will identify which are the analogous elements in electrical systems so that we can compare those with these mechanical systems, and whenever any mechanical system is given, how it can be converted into an electrical system. Okay, so today we will end this session with this summary.